This is the screencast for section 8.4, example 1. Improper integrals are what we're going to look at in this section. Improper integrals, meaning the integral is going to add up area that's infinitely long. How is that even possible? If it's infinitely long, wouldn't it be infinity? Not always. So first of all, the definition of an improper integral, they have infinite integration limits. Now to find these, so in other words, if f is continuous from a closed a to infinity, then the antiderivative from a to infinity, we can't just plug in infinity, take the antiderivative and plug in infinity. We're actually going to call it b as the upper limit, and we're going to take the limit as b approaches infinity. So you still have an upper limit of integration as infinity, but we're going to approach that as opposed to just plug it in. Same thing if you have the antiderivative from negative infinity to b. Now, if you have the antiderivative from negative infinity to infinity, we're going to split that into two and use number 1 and number 2. So negative infinity to c plus c to infinity. Now, one of two things are going to happen when you use these methods. Either your integral is going to converge, meaning the limit is an actual value, or if the limit fails to exist, the integral is going to diverge, meaning it has infinite area and we won't be able to find what it is. To better outline that process, let's say we're trying to find the antiderivative or the area under the curve between 0 and infinity of e to the negative x over 2 dx. So here's that graph, and we're trying to find this infinitely long area that technically is getting narrower and narrower as we approach infinity, but is still getting larger and larger a teeny bit. Well, first we're going to find the area out to b. So we're going to replace infinity with the antiderivative from 0 to b of e to the negative x over 2 dx. So we took the antiderivative, used fundamental theorem part 2, plugged in b, and then subtracted, plugging in 0, and we get this expression. Now we're going to take the limit of that area as b approaches infinity. So we're going to take b and continuously move it out forever and ever and ever and see what happens. Well, the limit as b approaches infinity of this, infinity over 2, is kind of infinity, but that's going to be in the denominator. So negative 2 divided by that is 0, and then plus 2 is 2. So our conclusion is that the antiderivative from 0 to infinity of e to the negative x over 2 dx is going to be the limit as b approaches infinity of the antiderivative from 0 to b of our integrand, and then that's 2. So let's look at our example. Now remember, in calculus, part of the challenge is being able to switch from one concept to another. So I just showed you an example that converges. This example is actually going to diverge, so let's show you how that works. Express the improper integral negative infinity to infinity of e to the x dx in terms of limits of the definite integrals, and then evaluate the integral. Alright, so first we want to find the antiderivative from negative infinity to infinity of e to the x dx. Well, we have the lower limit is negative infinity and the upper limit of integration is positive infinity. So we're going to split that at some value, and I'm just going to pick 0 because that's the easiest value. So I'm going to do antiderivative of negative infinity to 0 of e to the x dx, and then plus 0 to infinity of e to the x dx. Well, now we can't use infinities in our upper and lower limits of integration, so now we're going to change this first expression to the limit as b approaches negative infinity of the antiderivative of b to 0, e to the x dx, plus then the second one we're going to make b approach positive infinity of the antiderivative of 0 to b, e to the x dx. So this b is going further and further and further left, and this b is going further and further and further right to find out what happens to the how much area is under the curve from negative infinity to infinity. Well, by our instructions in the previous screen, the next thing I need to do is integrate. I need to find the antiderivative from b to 0 and from 0 to b. And then I'll use fundamental theorem part 2 in both of those expressions, and now I'll actually take that limit. The limit as b approaches negative infinity, so e to the 0 is 1, and then e to the negative infinity is going to be 0. Then over here, e to the infinity is infinity, and then you have minus e to the technically 0, which is 1. So as you can see, I get an expression with infinity in there, 1 plus infinity. Therefore, the integral diverges and the area cannot be found in this case. Now here's why. The graph of e to the x looks like this, and we're trying to find the area under the entire curve from negative infinity to infinity. Well, from 0 to negative infinity does in fact converge, because we found that in this left piece here, and that converges to an area of 1. So the area over here is 1. The problem is the area over here, it just keeps getting bigger and bigger and bigger and bigger, so you can't possibly figure out how much area is there. It's kind of infinite area, so therefore the whole thing does diverge. Now try problem number 3. Part A says express the improper integral as a limit of definite integrals, and part B says evaluate the integral. So again, we have this antiderivative from negative infinity to infinity of what looks like to be rational function. Now, since both our limits of integration are infinite, we need to split up the integral into the limit as b approaches negative infinity of the antiderivative from b to 0. I chose to split it at 0 just because 0 is easy to plug in. And then plus the limit as b approaches infinity of the antiderivative of 0 to b of the integrand. Now, I have to find the integral in this next step. So I'm looking at this thinking probably u substitution. So if I make u x squared plus 1, find du, solve for dx. Now I'm taking the antiderivative in both parts of this, so it's kind of convenient in that I can do my first step here on this left side. So now I'm going to take the limit as b approaches negative infinity of not b to 0 anymore, but u of b to u of 0. Of the antiderivative of 2x over, we're calling the inside of the parentheses here u, then squared, and then dx is du over 2x. Now, since I'm taking the same integral, I'm going to do the next step here. So now I'm going to take the limit as b approaches infinity of, now this time it's going to be u of 0 to u of b because I'm taking the limit as b approaches infinity. But now the inside, the integrand is staying the same, so I'm going to do the next step in that integral and simplify. So u to the negative 2, and then du, because the 2x is canceled out. Now in this next step, I can just go ahead and take that integral. So I'm kind of skipping a step if you in terms of left piece to left piece, but throughout my writing, I am going through the process. So I have now the antiderivative, which is the opposite of u to the negative 1, again from u of b to u of 0. And then I can evaluate that, plug in u, use fundamental theorem of calculus part 2. Now I'm going to take the limit as b approaches negative infinity of the first part, so I get negative 1 minus, well, 0. And then the limit as b approaches infinity of the second part, I get 0 plus 1. So it turns out that the whole area under this curve from negative infinity to infinity is 0. Interesting. Now if I look at a graph of the integrand, I can see that the area to the left side of the y-axis is under the x-axis, which is all negative, versus symmetrically positive on the other side, which therefore the areas to the left and to the right from negative infinity to infinity would cancel out and equal 0. So that does make sense.